So, welcome again. And our next speaker is Pankaj. He is from School of Mathematics, ISA Savendra, a PhD student, and he will speak on higher rank numerical ranges and unitary dilations. Please go ahead.
Yeah, thank you to the organizers for giving me an opportunity to talk here. So, and so it's a joint work with Mithun Mukherjee. So the overview of the talk would be I will talk about some brief introduction, then just this object for a normal operator, and from there for the description of in contraction using dilation theory and some references. So yeah, so we know that given a matrix, the quadratic form associated with A is defined as x star Ax. Now, the theory of quadratic form has been extended for an operator acting on a Hilbert space, which is known as the numerical range. And the numerical range is defined like that if T belongs to BH, where H is a complex Hilbert space and BH is the algebra boundary linear map, then a numerical range of T is defined by inner product of Tf, F, where if normal F is 1. So it has been studied extensively in the early 20th century because of its connection in pure and applied mathematics. One of the earliest property in the theory of numerical range is Wt is convex in the complex plane. Now Wt is always non-empty because Wt closure contains the spectrum, and spectrum is always non-empty. If T is a self-adjoint matrix with eigenvalue lambda 1 to lambda n, then numerical range is from the smallest to largest eigenvalue. And if T is normal, then Wt closure is closed convex along spectrum T. Just note that if T is finite dimensional, then Wt is actually always closed. So in that case, Wt is convex along spectrum. Now, if we want to get the closure-free definition of the numerical range of a normal operator, bit technical, we need a spectral measure, some concept, and that is a result by Dodds. He said if T be a normal operator and ET be the associate spectral measure, then Wt is intersection of convex Borel set S such that ET of S is identity. Okay, now let's go to the higher rank version of the numerical range, and it is called as higher rank numerical range. So let T belongs to BH and 1 less than equal to k less than equal to infinity, then k rank numerical range of T is defined as collection of those lambdas such that PTP is lambda P. Or in other words, T is unitary similar to the scalar matrix lambda identity star star star. Or we can say that exists an orthonormal set Fj such that Tfj, Fi is lambda delta Ij, where delta is a conical delta. Now, actually, it appeared in through the problem of error correction in quantum computation, and it has been defined by Choi, Krebs, and Zykowski. Mathematically, it has been defined. The moment it has been introduced, the people have started investigating the property what we know for the numerical range, whether it holds for the higher numerical range. Just note here, if k is equal to 1, then TFF is lambda. That means k equal to 1 actually gives a numerical range. Not only that, this is a decreasing sequence. And if T be a self-adjoint matrix, we noted before numerical range is from the lowest to the largest eigenvalue. There, just leave k minus eigenvalue from right and k minus 1 eigenvalue from left. So what we left with the k numerical range of T. Now they have conjectured the K-rank numerical range of a normal matrix in the same paper, which has been proven by Lee and Z, that K-rank numerical range of T is in intersection of convex hull of lambda J1 to J minus K plus 1. That means leaving K minus 1 eigenvalue, we are taking the convex hull of other N minus K plus 1 eigenvalue intersection that. So in fact, Lee and Z has proven more. They have proved that if T be a matrix, then lambda K T is actually intersection of some closed half plane determined by eigenvalue, some lambda K of this. So if K equal to 1, then actually it's very easy to observe. For example, if K equal to 1 is numerical range, if lambda belongs to numerical range, then a real part of e to the power I theta is also less than or equal to lambda 1, because numerical range of real part of T is real of W, real of numerical range of T. So that's why it's true. But for K greater than 1, this is actually proved is very non-trivial. Though the machinery what has been used only induction, but it's a very clever application of induction. And not only that, this result also says that as a closed plane is a convex grid, then the K-rank numerical range of a T is convex. So and actually for general operator, yeah. So general operator actually lambda K T is convex, proved by Wederman. So up to this, the theory is similarly like the numerical range. Now the actually deviation occurs. So just observe that if T be a normal of matrix of say lambda 1, lambda 2, lambda 3, if you compute the 2-rank numerical range, by the first result, what we will do, I will just leave one eigenvalue, take the convex hull of other in all possible way. So that will keep the K-rank numerical range is empty. So whereas K-rank numerical range could be empty, but a numerical range is always non-empty, that you observe. That is the bound. If 4k minus an 3 is less than or equal to n, then always K-rank numerical range is non-empty. Moreover, if T be an operator acting on an infinite dimensional Hilbert space, then K-rank numerical range of T is always not empty, but infinite numerical range could be empty. So what we are trying to do, we are trying to get an analog of this result for a normal operator acting on a infinite dimensional Hilbert space. And so just to define the closed half plane, it's actually a union of open half plane joined with a ray. For example, imaginary part is greater than 0. Union that positive ray is a closed half plane. And if lambda be the initial point of half ray, then we call it a closed half plane generated by the line delta omega at lambda. So T is a normal operator, and we are defining omega k T as intersection of H complement where dimension range of EH is less than K. See, just we are doing the same thing. We are just leaving K minus 1 eigenvalue and taking the intersection of the complement. And just quick some property that is convex because the intersection of convex set. This is non-empty for finite K, but infinity could be empty. And if lambda belongs to lambda K T, then whatever closed half plane you consider at lambda, the dimension is greater than or equal to K. We use this just quick proof. If that exists closed half plane whose dimension less than K, then omega K T is subset of H complement, so lambda does not belong to lambda K T, and other way also one can do. And infinity is intersection of lambda K T. Now it turns out that K-rank numerical range of a normal operator acting on a Hilbert space is this omega K T. So this lambda K T is subset of intersection, that is always true, but for the normal operator, this middle term actually lambda K T is subset of the middle term, that is always true. Equality occurs when for normal operator. Lambda K T subset of omega K T proof is not hard, but for the other direction we use the spectral theorem and few lemmas. So due to time constraint, I am not going to the proof. Later, just let's compute some example. There is a saying in operator theory: if some theory doesn't hold for shift operator, then there is no use. So let's compute the okay. That is the generalization of abundant result for self-adjoint operators. let's compute the k-rank numerical range of a shift operator. Shift operator you can think as the infinite dimensional matrix whose subdiagonal entries are 1. And this can be checked that eigenspectrum is empty and spectrum is T. Numerical range is D because WT is subset of D, and that can be checked. And we will notice that lambda k is a decreasing sequence. So lambda kt is subset of WT where WS is D. And for the other, let mu belongs to D. And what we have to show? We have to show mu is lambda kt. That means whatever half closed half plane we consider at mu, the dimension should be greater than or equal to k. So let's suppose H is a half closed half plane at mu. Now we'll claim that greater than or equal to k. If not, if dimension is strictly less than k from 0, then actually T S has eigenvalue because E omega commute with T, and if it is commute with T with respect to range of this is reducible subspace, so T S has eigenvalue, which is a contradiction. I mean, if it is 0, then it will contradict the WT, WS is D. So it's proved that k-rank numerical range of S is D. In fact, more general, if T is a normal operator with no eigenvalue, then all the numerical range are same. That actually one can prove. And just, yeah, that is another, there are many versions of spectral theorem. This one version is any normal operator can be viewed as a multiplication operator by a L infinity function. Let's take some easy multiplication operator. So this is a half square from real part of Z, imaginary part minus half to half. And we use a planar measure on R. And T is the multiplication operator, multiplication by Z. Then this eigenspectrum is empty and spectrum of this rectangle. As we are taking as a planar measure on R, then actually lambda kt is actually the open square. Subset is clear because lambda kt is always the closed rectangle, but all the point on the boundary doesn't belongs to lambda kt because there exists a half closed half plane. You can find the half closed half plane, dimension is 0. And other direction also can be proved by the similar way. Okay, so let's take another example. T is a direct sum of -1 by n e to the power I pi by n by n. So this is a -1 sequence converges to 0, and e to the power I pi by n is a point on the unit circle. As n tends to infinity, it is converging to 1, and we are dilating by n is going to 0. 0 is the point of accumulation. So eigenspectrum and spectrum are like this. And what you have to first show that 0 does not belongs to that numerical range, because for the point 0, if we take the lower half plane with the positive ray, then the dimension is 0. Hence 0 does not belongs to lambda numerical range, and hence doesn't belongs to infinity because it's a decreasing sequence. And if you take any non-zero point complex number, then dimension is finite, so doesn't belongs to lambda t, hence doesn't belongs to lambda infinity t. So then infinite numerical range is empty. So I said somewhat that infinity can be empty. So that is one example that infinite numerical range is empty. And if let's end this section by a corollary, if T be a normal operator, then lambda k is intersection of S where dimensional range of S complement is less than k. Just note here, if k is 1, dimensional range of ES complement is less than 1 means 0, then E of S is identity. That is exactly the Dirt's result which I mentioned in the first slide. So it generalizes the result, Dirt's result for higher rank numerical range. So from that, we are trying to describe the higher rank numerical range of a general contraction using the dilation theory. And the dilation is actually an operator S is said to be a dilation of T if it acts on a bigger space. Once I restrict S on H, it will get T. So if S is unitary, then S is said to be a unitary dilation of T. Now, the significance is that if there exists a unitary dilation, handling unitary operator is more easier. So though the price we have to give is we have to go the bigger space, but we can study the unitary operator and go back to this. And Halmos proved that every contraction has a unitary dilation. And that actually generates a lot of research, including Nash dilation theorem, who said that if T is a contraction, T has a dilation. Not only that, every power of T is also a power dilation. But anyway, that is a different research area and operator theory. Just to straight to the higher rank numerical range, this is easy to observe that lambda kt is subset of lambda ku, and u is a unitary dilation of T. Now it is now natural to ask whether the equality occurs on. So Gaulian, who proved that if T is a matrix, then equality occurs, and U actually n plus dt, and that is the maximum one can hope. So we asked whether this is the same kind of equality occurs for an operator acting on a infinite dimensional universe space, and the answer turns out no. So that is the example. So let's take just a half circle. Imaginary gamma is a those z in C, imaginary part of z is greater than or equal to 0. And let's open circle denoting as R, that half open half circle. And then lambda kt is subset of R union 0, because by our main theorem, if you take any point on the unit circle, then there exists a half closed half plane dimension is 0, and other direction is also one can prove. So it is then lambda kt is R union 0. Now, if you take U is any unitary dilation of T, then actually as T is using unitary dilation of T, then lambda kt is subset of lambda ku, and lambda kt will compute R union 0. So lambda kt is always contain R union 0. But it can be proved the interval -1 to 1 also be a part of lambda ku. That can be actually proved. So it says this is R union 0, but -1 to 1 contains in every lambda q. So this is a proper containment. So next natural thing to ask is when the equality, what would be the condition we should impose, necessary and sufficient condition so that equality occurs. If you observe here for the point 0, there does not exist any closed half plane whose spectral dimension is less than k, and that turns out the equivalent condition for the equality to occur for the normal operator. And just quick sketch. So for k equal to 1, the same condition has been given by U, and that condition turns out only necessary, not sufficient. So our condition not only rectifies the mistake, but also generalizes for the higher function. So let's okay. So I'll just skip the proof. This proof. Yeah. So now for a normal operator what is the for general operator for the condition what is given for normal operator, that is for we can use the spectral measure, but for general T doesn't have a spectral measure. So we'll just see that real part of this and that condition. So we have proved that this condition is necessary in the paper, but the sufficiency part we could not able to prove. And the problem lies for k equal to 1 case. K equal to 1 case, the condition is equivalent to WT subset of an open half plane, and that condition is actually equivalent can be proved for a very large class operator. For example, if T is a finite index, then actually these are equivalent. And if T is a shift operator, that is also equivalent. So we conjecture it, and we are working with it. But if we take the closure, then these set are actually equal. For infinite numerical range, it is equal if it is non-empty. An example can be given that if it is not non-empty, then this is not proper subset. And if T is a contraction with same and finite different indexes, then you can be actually taken in a smaller space, that H directs some Ci. And the main result we use to prove this is Barkovich and Timothy unitary dilation result. And these are the talk has been made based on the reference 1. The last 2 result appears in reference 2, and these are the other references. And thank you very much for your attention.
Any questions from the audience or online participants? Can you check? One small query from my side. So what is the significance of this higher range numerical range for contraction methods?
Significant, actually, it appeared in the what I mentioned in the quantum computation, as that is the relation between the numerical range when to because computing the k rank numerical range is difficult. So that's why we are actually giving a path, a direction. Because what in the first part we saw how computing the numerical range, higher numerical range for a normal operator can be computed. So not unit operator, normal operator, so that can be also computed. From there, whether it can be computed for a contraction. That is the one. Actually, for k equal to 1, that is a conjecture by Helmholtz that WT is intersection of W. So similar kind of we are hoping here. So in general,
maybe you can extend that to companion the contractions are everywhere. in mathematics and in many fields. Yes.
And contraction we take because of every contraction has immediate dilation. That is one reason.
Okay. Good. Thank you. Okay, let us thank then. I think this is all.